Hello friends, this is Jim with Science Talk. This is the second in a series of videos I'm making about oceanic current circulation. The next one I wish to discuss with you is the North Atlantic Ocean currents are slowing. The North Atlantic currents, which help to warm the northwestern Europe and Scandinavia regions, have slowed significantly since the last century, scientists confirm. Okay? As I just mentioned this in the first video in this series. The Gulf Stream is slowing. The North Atlantic is cooling. An international scientific study has found new and harder evidence that one of the planet's key heat pumps, the currents which exchange warmth between the tropics and the Arctic, are weaker today than at any time in the last 1,000 years. The currents known as the Atlantic overturning. Its scientific name is the Atlantic Meridional Overturning Circulation, the AMOC, or AMOC. Bring warm water north from the tropics, return south with cold water. Now, kind of a spoiler alert here, but I am one of those oceanographers who is of the opinion that global warming will bring on an ice age. I know that sounds paradoxical, but as you will hopefully see in these two videos, in the next bunch of videos, why I think this is the case. Earlier studies suggested strongly that any weakening of the AMOC would speed sea level rise on the U.S. East Coast and cool northwest Europe by up to 5 degrees C. That's basically 9 degrees Fahrenheit. That is significant. That's enough to throw into at least a mini ice age, or if not, if a full blown out ice age. Now, of course, the studies are making use of computer simulations, but the latest research is radically different. It is based on direct observation on what is happening in the ocean. And it is, in non-scientific language, hard evidence that the Gulf Stream is slowing down. Now, in the first video in this series, I mentioned how the northern end of the Gulf Stream terminates in the Jin Sea, the Greenland, Icelandic, Norwegian Sea. It gives off its heat to the atmosphere, becomes cold, and it sinks. Okay. So the density of seawater. Now let me back up first. The density of fresh water is determined by temperature. The cooler the temperature is, the more dense fresh water is, to a point. Fresh water is most dense at 4 degrees Celsius. And that is because of the interesting nature of the arrangement of the hydrogen and oxygen atoms within the water molecules, as well as the angle, about 108 degrees. The fact that it is a polar covalent bond and its dipole moments and so on and so forth, and the nature of the hydrogen bonding all lead to the fact that at 4 degrees C, fresh water is at its most dense. You cool fresh water past 4 degrees C to 0 degrees C, you get ice. But water at that temperature is less dense. Now, as it forms the ice, the water actually starts to expand. This is why ice floats. Were it not for this interesting molecular arrangement, an atomic arrangement, all the lakes and oceans on the planet would be big frozen ice cubes. Frozen solid. But because of that, ice is then less dense. Now, the density of seawater is determined not just by temperature alone, but also by its salt content, which we call salinity. And we can measure that. So basically, if I have two bodies of water, and let's say they're both 15 degrees C, okay? But now this body of water has a salinity of 32 parts per thousand. That's how we usually measure salinity. And this body of water has a salinity of 34 parts per thousand. Same temperature, this body of water, because it has a higher salinity, will be more dense. So if we were to mix that, there will be a little mixing, intermingling, but eventually that body of water would go sink below the other body of water. So the Gulf Stream is already a salty water. In fact, on average, the salinity of the Atlantic is about 33, 34 parts per thousand, whereas the Pacific is 32, 33 parts per thousand. So there is a difference in salinity of about 1. May not sound like much, but that is significantly different enough to cause circulation patterns. Because the waters of the Arctic Ocean do communicate with both the Pacific and the Atlantic side. Even that's at least on the surface. You have the Lomonosov Ridge, which creates two basins, but that's a whole nother story, and that's not really pertinent or relevant at hand to what I wish to discuss with you at the moment. So, if I now have this Gulf Stream, which is warm, salty water, it now gives off its heat. It now becomes cold, salty water. It's extremely dense. It just sinks vertically right down. Now, researchers at Dalhousie University, which is located in the twin city of Halifax, Dartmouth, Nova Scotia, have measured a slowdown in what we call chimney formation. Yes, we kind of come up with cute names here. But basically, they have measured a slowdown in the deep water formation. Because when this Gulf Stream water cools off and sinks, it sinks down vertically, and it returns as what's called the North Atlantic Deep Current, or North Atlantic Deep Water. That's the return flow. That's what we're talking about here, bringing the cooler water from the Arctic region back to the tropics. In essence, the Atlantic meridional overturn circulation is the start of the conveyor belt. I'll be discussing that in greater detail in the next video. So there has been studies that have direct observations have measured slowdowns in the deep water formation, and now we're seeing slowdowns in the actual flow of the Gulf Stream itself, which would tie into, if the deep water formation, the sinking is slowing down, so will the surface flow slow down. So, a team from Germany's Potsdam Institute for Climate Impact Research, commonly called PIK, and the U.S. National Oceanic Atmospheric Administration have found evidence which says not only supports the earlier predictions, but makes them hard to dispute. In a study that is published in the journal Nature, the researchers say analysis of sea surface temperature data shows that the AMOC has slowed down by roughly 15% since the middle of the 20th century, with human-made climate change a prime suspect. We detected a specific pattern of ocean cooling south of Greenland and unusual warming off the U.S. coast, which is highly characteristic for a slowdown of the Atlantic overturning, also called the Gulf Stream system. This is from the lead author, Levke Caesar from PIK, who goes on to state it is practically like a fingerprint of a weakening of these ocean currents. For decades, computer simulations have generally predicted that the AMOC will weaken in response to human-caused global warming. Okay, that's what computer models say. And it was unclear for quite some time whether this is a possibility. You know, it's one thing to do computer modeling, but now we have data, direct observations that are now supporting this hypothesis. The evidence we're now able to provide is the most robust to date, says Stefan Rahmstorff of the Potsdam Institute, who basically conceived the study. We've analyzed all the available sea surface temperature data sets comprising data from the late 19th century until the present. The specific trend pattern we found in the measurement looks exactly like what is predicted by the computer simulations as a result of a slowdown in the Gulf Stream system, and I see no other plausible explanation for it. I just mentioned this, but I'll repeat it again. The Atlantic overturning is driven by the differences in the density of the ocean water, when the warm, lighter water flows from south to north, it becomes colder, denser, heavier, making it sink deeper and flow back southwards. Now, as I will mention here, we are now melting piles of Greenland ice sheets. We are now putting this layer of fresh water on the ocean surface. What will that do to the Jin Sea? You have the Gulf Stream terminating, giving off its heat, but now, yes, it's cold, but now it is not as salty. It's not going to sink as much. This is part of the reason that there's been direct measurements of this slowdown in the overturn here. Because one of the biggest things that we study in oceanography is, what if I have cold, less salty water versus hot, salty water? Which is more dense? You get some interesting mixing. And we develop what are called TS curves, temperature salinity curves, where if we see a range of values in both temperature and or salinity, that's typically indicative of water masses mixing. Whereas if you see a point, and that's pretty much you can identify, well, that's this particular body of water. It could be the Western Pacific equatorial current, what have you. But you can you can almost, using what's called temperature salinity signatures, you can identify specific water masses. But when they would meet and start mixing, then you get some really interesting fluid dynamics going on. Global warming, it should be noted, is not the only influence on the AMOC. Increased rainfall and meltwater from the Arctic sea ice and Greenland ice sheet are also diluting the waters. I just mentioned that. Less saline water is less dense and so less heavy, making it less likely to sink, or if it does sink, not as deep. Because as water sinks, there's also buoyancy forces underneath, and it will sink until it finds basically similar temperature salinity characteristic, and then the water will be held up by buoyancy forces that will counteract any gravitational influences. So if it's less salty, it may sink, but it won't go as far deep as it typically has, and it may not result in the return flow that we historically have observed. There have been long debates about whether the AMOC could collapse, which would constitute a tipping element in the Earth system. The PIK study does not consider the AMOC's future, instead analyzing how it's changed over the past century. Now, I will be discussing in the next video how there has been complete collapses of the AMOC. And every time the AMOC collapses, an ice age results. So that's the next video. A second study by a team including David Thornley from University College London in the same issue of Nature looks into the Earth's past climate to reconstruct Atlantic overturning changes over the past 1,600 years. It provides independent confirmation for earlier conclusions that the weakness of the circulation today is unprecedented for more than a millennium at least. Several lines of evidence are coming together to a consistent picture now, all pointing at the same weakening since the 1950s, says Professor Ramstorff. They include subpolar Atlantic cooling, the warming inshore of the Gulf Stream, Thornley's proxy data for subsurface Atlantic temperatures, and early proxy data from deep sea coral showing water mass changes in the Gulf of Maine. So, where I will be taking the next video in this series is an actual discussion of the ocean conveyor belt. And I will be discussing the very important work of Wally Broecker. And I think you'll find this extremely interesting. Thank you for your time. I hope you've enjoyed this video. Please share it, subscribe, hit the bell. Become a patron at patreon.com/Science Talk with Jim Massa. If you're already a patron, thank you for your continued support. On to part 3.